Aloha class, here we go. We're on section 3.4 now, velocity and other rates of change. So this one here is a real important one when we get to the AP test at the end of the year. One, because a lot of students make mistakes here, and we look at graphs and we have to get really familiar with graphs. So to get started here, now my notes are going to be a little bit differently than yours. I think most of yours will be typed out. So I ask you to take some additional notes. Anything that you see important, please make sure you're taking a little bit of additional notes. All right, so here we go. Just with some definitions here. Motion along a line. Since calculus is the study of how things change and a derivative is a rate of change, we can now use derivatives to describe motion along a line. We will only study horizontal and vertical motion along a line at this time. All right, here we go. The important thing we need to know is the relationship between position of a function, velocity of a function, and acceleration of a function. All right, position. S of t, or sometimes in AP Calc we use x of t, describes the position s of an object after t seconds. The displacement of an object is the change in position over a given time interval. On the position graph, okay, once again, you're going to see it's very important to understand what graph you're looking at. If I'm doing a problem and it has a little s up here, then that means it's the position graph. We can easily determine the direction an object moves. When s of t is increasing, we say it's moving up or it's moving to the right. When s of t is decreasing, we say an object is moving down or to the left. Now, position is very important. What's also important when we get to AP Calc is what we call velocity. And it's assumed, even though we're never supposed to assume, it is assumed in AP Calc that when we reference velocity, we are referring to instantaneous velocity, right, class? Which would mean the slope of a secant line or the instantaneous rate of change. And it describes the rate of change in the position, and v of t, our relationship, is equal to the first derivative of position. Unless we say the word average velocity, we're going to assume, like I just stated, that it's instantaneous velocity. It is the slope of the tangent line to the position function, aka the derivative. All right, here we go. On a velocity graph, once again, we're going to be looking at all kinds of graphs. Sometimes it'll be an S. Let's say this one has a v of t, which means it's a velocity graph. We can determine the direction an object moves. When our velocity is greater than 0, the object moves in a positive direction, up or to the right. When our velocity is less than 0, the object moves in a negative direction, which is down or to the left. When v of t is equal to 0, the object is stopped. Now, velocity is a vector quantity and must have magnitude and direction. Thus, the plus and the minus are important for us interpreting it. However, if we reference the speed of an object, how fast it's going, okay, then that's the absolute value of velocity, and speed is always positive. Acceleration. Let's bring acceleration into this bad boy now, right? If I'm hitting on that gas pedal and I vroom, vroom, vroom. All right, here we go. Acceleration. Or, once again, it's assumed that we're speaking of instantaneous acceleration. Describes the rate of change of velocity. Thus, this little relationship is very important. Acceleration is the first derivative of velocity or the second derivative of position. We can use the velocity and acceleration to determine the following: when an object is speeding up or when it is slowing down. All right, we say it is speeding up when velocity and acceleration have the same sign. Here's our justification, right? With velocity and acceleration are both positive, we say it's speeding up. Why? Because they have the same sign. When velocity is negative and negative, same thing. Whether they're both negative or both positive, we say it's speeding up. Vice versa, when an object is slowing down, velocity and acceleration will have opposite signs. How do we justify that? Well, if velocity is positive, acceleration is negative, our object is slowing down. Otherwise, if velocity is negative and acceleration is positive, then that means our object is also slowing down. Remember, since velocity and acceleration are derivatives, they are rates of change and should always include units. We always want to put units even if they don't ask. For this rate of change according to the information given in the problem. Also, when we describe a derivative, we need to include the point, of attachment in our answer in order to receive credit. What the heck does that mean? Don't worry about it. We'll do some examples shortly. Okay, so let's go ahead and look at our little Bugs Bunny and Yosemite Sam. Okay, and it says you can use a calculator in AP Calc. Whenever it says you can use a calculator, go ahead and use that calculator. Now, how do we start using our calculators in AP Calc? One, whenever they give you an equation, go ahead and plug that bad boy in Y1. All right, and then see, I challenge you. Okay, I gave you some definitions of these things. Let's see if you can hit that pause button and answer these questions without my help. Okay, hit that pause button. But I'm going to get started right now for anybody that doesn't want to be challenged. All right, what is Bugs' displacement from t equals 1 to t equals 2 seconds? Well, if we look back to our definition, displacement was our change in position. So I already have my answers right here on my sheet, so I'm going to take a little peekaboo. Okay, but you can easily put this in your calculator, right? Our change in position would be s of 2 minus s of 1. And if you plug that bad boy in your calculator, we get negative 32 feet. So that would be your displacement. Remember, and the negative means we went to the left or we went down. In this case, since I'm jumping off, I'm going down. Okay, when will Bugs hit the ground? Well, there's a couple ways we could do this. Hopefully we understand that Bugs is going to hit the ground when our position is equal to 0. So what I could do is I could take my s of t, which is negative 16. Sorry, class, I had to go over to this screen because the marker went out again. And I didn't want to reset this video, so I apologize. But I will go slowly, okay? But when will Bugs hit the ground, right? When our position is equal to 0, so I'm going to set that function equal to 0, right? You could use your calculator, right, and graph and find out when that guy crosses also that t-axis. But I could do this one by hand, okay? And so by factoring this thing, my marker went out again, so I apologize. So it'll be nice that I have these answers up here. I will come over here, okay? But I get two answers. I get t equals 5 or t equals negative 4. Well, since I can't go backwards in time, right, class? We cross out that bad boy, and my answer would be t equals 5 seconds. That's when Bugs hit the ground. Ouch! 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 All right, here we go. C. When is Bugs' velocity? What is Bugs' velocity at impact? Well, this is when we start using that relationship, okay, that we have between acceleration, velocity, and position. And I want to know, if I want to know what is Bugs' velocity at impact, well, I'm just going to find out what v of t is equal to. And v of t, remember, is the derivative of position. So first derivative would be negative 32t plus 16. Okay, and then at impact, well, impact is after 5 seconds. So I find v of 5, and it's 144 feet per second. Why feet per second? Because once again, okay, I'm always going to include my units. And it's change in your position over the change in time, which would be feet and seconds. What is Bugs' acceleration as a function of time? Well, the acceleration, again, is the first derivative of velocity or the second derivative of position. So if I take the derivative of velocity, I would get negative 32. So the acceleration, probably because of a little gravity, right, is negative 32 feet per second squared. Once again, that would be your units of velocity over time, right? Your change in velocity over change in time. And velocity is feet per second. Over time would be seconds, feet per second squared. Booyah! And you guys, I know, have dominated in your physics classes, so that units is probably pretty okay for you. All right, here we go. Marker's still not working. I apologize. So I'm going to keep this up here just so it's more legible, okay? Which way does the particle move first? Okay, if we look at our graph, and it's very important that you guys pay attention to that. This is without a doubt the velocity graph. Okay, and it's important to circle that guy 1, 2, maybe 3 times. Okay, and when I circle that one 3 times, it helps me to focus what I'm looking at. And if I want to know whether I'm moving left or to the right, I want to know what my velocity is. And since my velocity is negative down there, that means my velocity is less than 0, which thus means my particle is moving to the left first. Okay, when does the particle stop? Well, when we look back at those definitions we wrote earlier in this lesson, velocity stops when our velocity is equal to 0, and it's equal to 0. People forget at t equals 0, t equals 3, t equals 7, and t equals 10. All right. When does the particle change direction? Now, a lot of people miss this one, so let me get rid of some writing here. But we change direction whenever velocity changes signs. And there's only one time velocity changes sign. It's right there, right, class? It gets back to 0 there, but it doesn't change signs, right? It stays negative. So we do stop there. But I want to know when my particle changes direction. And it changes direction at t equals 7. Why? Because it changes from negative to positive. Okay? And I have the explanations written out beautifully here, and you won't have to look at my handwriting. You guys let me know in class. Do you like having these notes pre-written, or would you rather me write them with you? Okay, remember, I've already told you how much I don't like this little U tail. Okay, don't do that. Union is that symbol. Kind of, sort of. Let's make it prettier. There we go. All right, when is the particle moving left? When is it moving to the right? Oh, snap. Let's bring that bad boy down. We can't answer that question without our graph right there. Okay, the particle is moving to the left from 0 to 3. Okay, let's make it blue. From 0 to 3, union, 3 to 7. Why? Because velocity always justify is less than 0. When we're moving to the right, we're moving to the right, 7 to 10. Why? Always give that justification. V of t is greater than 0. All right, it says the graph. Now, I know some of you, this is going to take you for a loop. What I challenge you, please do it. Try to graph this bad boy without looking at my answers that are already on this board. Once again, we're going to circle that guy 3 or 4 times. We're going to do an acceleration now. An acceleration is the derivative of velocity. Oh, snap, bring that bad boy back. That's the only way to graph it. All right, so let's graph this bad boy. How do I graph it? Well, acceleration, class, is the derivative of velocity. Well, if it's the derivative, oh snap, that means it's the slopes, right? And let's look here. What are the slopes there from 0 to 1? The slopes are down 1 over 1, which would be negative 1. That's why we graphed it right there. Okay, boom, boom. And my graph's not going to be as good, okay? What are the slopes from 1 to 3? That looks like up 1 over 2. That's why we have that graphed at 1/2, okay? Hopefully it's making a little bit of sense. I apologize again that I can't do it with you guys, okay? Whoa, snap. That's down 4 over 1. That's why we're all the way down here at negative 4 on the acceleration, okay? Oh, snap. That looks like we have a horizontal tangent. That means we have slopes that are 0, right? And we always have these open circles here. Why? Because it changes there. Okay, what is it from? Oh, that's a long lengthy. That's from 5 to what? 5 to 8? From 5 to 8, it looks like it's up 2 over 1, up 2 over 1, up 2 over 1. That would be 2. That's ni in Japanese. Okay, and then what do we got right there? From 8 to 9, it's a positive 1. So we go there, and then, oh, snap, we got negative. That's down 3 over 1. That's why we're at negative 3. Okay, I'm going to go ahead and erase that bad boy so we can get to the next one. Once again, make sure you hit pause to make sure that makes complete sense. Okay, what are we asking next? Oh, snap, I need both graphs for that too. Okay, when is the particle speeding up? Well, let's go back to those notes. When could a particle be speeding up? Well, look at my justification. When velocity and acceleration have the same exact sign. Well, when would velocity and acceleration have the same exact sign? Whenever they're both negative or both positive. So looking at these graphs are very helpful. Remember, this is velocity right here, okay? And this is acceleration right here. Well, where are they both negative? They're both negative from 0 to 1, okay? They're both negative, right, class? And from 3 to 4, 3 to 4, right? They're both negative. That's why it's speeding up. Well, it could also be speeding up when they're both positive. Well, where are these guys both positive? From 7 to 9, velocity is positive, and from 7 to 9, acceleration is positive, okay? Now, when is it slowing down? Let's go ahead and check this out. I can make it blue. It's slowing down when velocity and justifications, class, are so important, so pay attention to the way we write these answers, please. Velocity and acceleration the particle slowing down when there are different signs. So different signs would be when velocity is negative, but acceleration is positive. There we go. Velocity is negative. Acceleration is positive. Okay? And from 5 to 7. 5 to 7, velocity is negative. Why? Because it's below. But from 5 to 7, acceleration is positive. Or I should say, when velocity is positive and acceleration is negative, which only happens one time. Look at that. Velocity is positive. Why? Because it's above. But it's negative because it's below. Hopefully that was okay. For a lot of students, that's really tough for them to understand. And don't you worry, We flip that classroom, flippy flip. So we will practice that tomorrow in class. Once again, my apologies, class. Last little bit of notes here. Okay, we're going to graph the speed. Well, how the heck do I graph speed? Well, if we take a look back here, okay, I'm going to go here. All right, remember, speed is the absolute value of velocity. So what it is, and I'm not going to be able to do a good job of this, but we just flip. Anything that is negative, right, we went up 4. Anything that was negative, we come back here and we make it positive. So that red would be the graph of speed, right? We kind of get rid of all this negative stuff because speed is the absolute value of velocity. Here is it nice and pretty, okay? Which that's all we're doing for that bad boy. Okay, class, is we're taking that velocity graph and anything that's below, we put it above the t-axis. Okay? When is the particle moving the fastest? Well, it's moving the fastest whenever it has the fastest speed. And the fastest speed would be from 4 to 5. Why? Because that has a speed of 4, right? Feet per second squared. Okay, which is the absolute value. Okay, all beautifully laid out right there. When is the particle moving at a constant speed? Well, if you notice, boom, 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 constant, boom, 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 right? So the only constant speed would be 4 to 5. Okay, and that would be whenever your acceleration is 0. Okay, and your acceleration would be 0 whenever the derivative of velocity is 0, which would be the tangent line. There you go, horizontal tangent. All right, some ridiculously important notes right here. I'm going to, so important, boom, boom, boom. Okay, let me get rid of that. Sorry, getting a little crazy over here. All right, getting mad at my pen not working. This pen not working. All right, some general but important reminders. Justifications, never use the word it. Don't use the word it. Describe the function as f of x, s of t, v of t, a of t. Always tell your AP grader what you are referencing. Always describe a derivative, aka instantaneous rate of change, using units as a ratio and a point of attachment. Okay, so a point of attachment would be like, what's the velocity at t equals 5? There we go. There's my point of attachment. We are using first and second derivatives for velocity and acceleration, but that is one application. Okay, you'll find out later what we mean by that guy. Let the reason why dictate whether or not you are going to include the endpoints of an interval. Your answer must have integrity. And last, label all graphs you draw with a function name, a derivative name or a second derivative name, right? Are you looking at position graph? Are you looking at the speed graph? Are you looking at a velocity graph? Are you looking at the acceleration graph? Please, class, if you want to be successful in AP Calculus, you have to be doing the extra worksheets at home. Work on those bad boys. Practice. Well, perfect practice makes perfect. Aloha.